Melting is the initial stage in silver manufacturing, where silver is heated to its melting point, often mixed with other metals to achieve the desired purity and strength. This molten silver is then poured into molds or cast into ingots for further processing. Sheet making involves passing silver through rolling machines to create uniform sheets of desired thickness for further crafting and shaping. Stamping uses a power press machine to shape silver sheets into trays, plates, and other items. Dies and molds define the final form, ensuring precision, consistency, and intricate detailing in mass production. Metal spinning shapes rotating silver discs or tubes into symmetrical hollow forms using high-speed force, creating bowls, vases, and other cylindrical objects. Hand shaping involves hammering silver to create unique, intricate designs. Soldering joins silver pieces using heat and filler metal for durability. Embossing nakshi creates raised patterns on silver using specialized tools. Hand scratching etches fine details onto silver surfaces using sharp tools. Cut work jali work involves cutting intricate patterns into silver surfaces. Engraving is the process of incising intricate designs onto silver surfaces using sharp tools or machines. This technique enhances aesthetics, adds personalization, and creates detailed patterns, often used in jewelry and decorative items. Casting involves pouring molten silver into a mold that defines the desired shape. Once cooled and solidified, the piece is removed, refined, and polished. This method allows for intricate designs and mass production of silver items with consistent quality. Hand filling smoothens and shapes silver using specialized manual tools. Buffing machine polishes silver surfaces using rotating wheels and abrasive compounds. This process enhances smoothness, removes imperfections, and creates a high-gloss, reflective finish, improving the final appearance of silver products before distribution. Electroplating coats silver with a thin metal layer using an electric current, enhancing durability, appearance, and resistance to tarnishing. Annealing softens silver through heat treatment, improving workability, while cleaning removes impurities, ensuring a smooth, polished final product. Packaging and dispatch ensure silver products are safely packed for protection during storage and transportation. High-quality packaging prevents damage, maintains shine, and enhances presentation. Proper labeling and logistics management ensure timely delivery to customers, maintaining product integrity and satisfaction. In the cutting step, high-quality steel is precisely cut into shovel blade and handle shapes, using advanced machinery for uniformity and strength. In the sharpening step, the shovel blade's edge is finely ground and honed to ensure optimal cutting performance, durability, and penetration efficiency. In the forming step, the pre-cut steel is heated to high temperatures and pressed into the desired shovel shape using powerful hydraulic or mechanical presses. This process ensures structural integrity, precise curvature, and a strong ergonomic design for durability and efficient use. In the quenching step, the formed shovel is heated to a high temperature and rapidly cooled in oil or water. This process hardens the steel, significantly improving its strength, wear resistance, and durability against bending or breaking. In the quality check for quenching, the hardened steel is inspected for proper hardness, uniform cooling, and potential defects to ensure durability and strength. In the tempering step, the quenched steel is reheated to a controlled temperature and then slowly cooled. This process reduces brittleness while maintaining the required hardness, ensuring the shovel remains strong yet flexible. Proper tempering enhances impact resistance, preventing cracks or fractures during heavy use. This critical step balances durability, toughness, and long-term reliability. In acid cleaning, impurities, scale, and oxidation are removed. In the cutting step, Steel pipes or rods are precisely cut into designated handle lengths, using automated machinery to ensure uniform size and consistency. In the grip manufacturing process, a durable and ergonomic grip is crafted to ensure comfort and control. The grip material, often rubber or plastic, is molded or wrapped onto the steel handle for a secure hold. It undergoes shaping, texturing, and quality checks to enhance user comfort, prevent slipping, and withstand prolonged use in harsh conditions. In the welding step of the shovel handle process, the pre-cut steel handle is securely attached to the shovel blade using high-precision welding techniques. This step is crucial for ensuring the overall durability, strength, and longevity of the shovel. Before welding, both the shovel blade and handle undergo surface cleaning to remove any rust, oil, or contaminants that could affect weld quality. The handle is positioned accurately in alignment with the blade to ensure proper balance and stability. Automated robotic systems perform welding using advanced techniques such as MIG, metal inert gas welding, or arc welding. This process fuses the handle and blade together, creating a seamless, high-strength bond. The weld must be deep and consistent to withstand extreme pressure and heavy-duty use. After welding, the shovel is allowed to cool naturally or through controlled cooling to prevent warping or structural weaknesses. The welded joint is then thoroughly inspected for cracks, inconsistencies, or weak points. Any defects are corrected to ensure maximum durability. For additional strength, reinforcement welding or extra layers may be applied. This ensures that the handle remains firmly attached even under extreme stress, making the shovel resistant to bending or breaking. In the painting step, the shovel handle and blade are coated with a protective layer to prevent rust, enhance durability, and improve aesthetics. The process involves cleaning the surface, applying primer for adhesion, and spraying high-quality paint or powder coating. After drying and curing, the painted surface is inspected for uniformity, ensuring a long-lasting and corrosion-resistant finish. Across many regions of Africa, the art of making aluminium cooking pots by hand remains an important and skilled craft. These durable and affordable pots are made using recycled aluminium, such as old engine parts, spoons, and other discarded metal objects. The process is a combination of traditional knowledge, creativity, and craftsmanship. To form the mold, artisans first create a pattern, which serves as the base for the pot's design. The mold is built in two halves, allowing the pot to be easily removed after casting. A small piece of tin is placed inside the mold to prevent the aluminium from sticking. The mold is carefully packed and shaped, ensuring there is an air gap that allows the molten metal to flow smoothly. Once the mold is complete, a hole is made at the top where the molten aluminium will be poured. The two halves of the mold are then tightly joined together, ensuring they align perfectly for a well-formed pot. Before pouring the metal, a layer of ash is dusted inside the mold. This helps prevent defects and makes it easier to remove the finished product. The first step in making aluminium pots is gathering the raw materials. Craftsmen collect aluminium scraps from various sources, including old car parts, broken utensils, and discarded household items. These pieces are melted down in a makeshift furnace, reaching extremely high temperatures until they become a molten liquid. The process of melting aluminium is both intense and fascinating. The metal scraps are placed in a fire, which burns at extremely high temperatures, turning the solid pieces into a glowing red-hot liquid. The molten aluminium is then carefully poured into the prepared mold through the designated opening. As the metal cools, it takes the shape of the mold, solidifying into a durable cooking pot. To speed up the cooling process and prevent imperfections, a small amount of water is sometimes applied to the mold. Once the aluminium has completely hardened, the mold is broken open, revealing the newly formed pot inside. After removing the pot from the mold, The craftsmen clean off any excess sand and smooth out rough edges. In some cases, the pots are polished or lightly sanded to improve their appearance. Handles and other finishing touches are sometimes added, depending on the design. This traditional method of making aluminium pots is not only practical but also highly sustainable. By recycling old metal scraps, artisans reduce waste while producing essential household items. These handmade pots are widely used across Africa for cooking thanks to their durability and ability to retain heat effectively. Mold making is the first and one of the most critical steps in the traditional aluminum pot making process in Burkina Faso. It determines the final shape, size, and texture of the pot. The artisans use a method called the green sand technique, which involves creating a temporary mold using a mixture of fine sand, clay, and water. This method is widely used because it is cost-effective and allows for intricate detailing on the final product. The artisans begin by selecting fine, high-quality sand, which is then mixed with clay and water. This mixture must have the right consistency, moist enough to hold its shape but not too wet, as excess moisture can cause defects in the final mold. The sand is sifted and kneaded thoroughly to ensure it is free of impurities that could affect the smoothness of the cast pot. A pattern or model of the pot is used to shape the mold. This pattern is typically made of wood or an existing aluminum pot. The model is placed in a wooden or metal frame called a molding box, which holds the sand in place during the molding process. The sand mixture is carefully packed around the pattern, ensuring that it fills all spaces and captures the details of the design. Artisans use their hands and compacting tools to press the sand tightly. Once the mold is packed, it is divided into two halves, the top half, cope, and the bottom half, drag, to allow for easy removal of the pattern. After the sand is firmly compacted, the artisans carefully remove the pattern from the mold, leaving a hollow cavity in the exact shape of the pot. If the sand is too loose or too dry, the mold may collapse, requiring the artisan to start over. Before the mold is ready for casting, the artisans create channels called sprues and vents to allow molten aluminum to flow in and air to escape. This ensures a smooth and even cast. Once the mold is prepared, the next crucial step is melting the aluminum. Artisans collect scrap aluminum from old engine parts, cans, and other discarded materials. These metal pieces are broken down into smaller chunks to ensure even melting. The aluminum is then placed in a crucible, a heat-resistant container, and heated in a traditional furnace fueled by charcoal or wood. The furnace reaches temperatures above 660 degrees Celsius, 1,220 degrees Fahrenheit, the melting point of aluminum. To ensure a clean melt, artisans use improvised tools to skim off impurities and dross, oxidized metal, that rise to the surface. Once fully liquefied, the molten aluminum is carefully poured into the prepared mold, marking the next stage of the pot-making process. Once the aluminum is fully melted, artisans carefully lift the crucible using tongs and pour the molten metal into the mold through the sprue entry channel. This process requires precision to ensure a smooth fill without air pockets. The metal flows into every cavity, shaping the final pot structure. After the molten aluminum has cooled and solidified inside the mold, artisans carefully break apart the sand mold to reveal the newly cast pot. Since the mold is single-use, it is destroyed in the process. Any excess aluminum, such as sprues or rough edges, is trimmed off. The pot is then cleaned, sanded, and polished to achieve a smooth finish before being ready for use. Aluminium recycling is a crucial process that contributes significantly to environmental conservation and resource efficiency. The process involves reclaiming aluminium from various sources, such as old window frames, beverage cans, and automobile parts, and transforming them into new products without the need for primary aluminium. This reduces energy consumption and minimizes environmental impact. At Hydro Aluminum Recycling in Dagan, engineers have developed a highly efficient recycling system that closes the loop by ensuring that aluminium can be recycled into the same products it was originally used for. The challenge of aluminium recycling. Aluminium is composed of numerous alloys, each with different properties. Traditionally, when scrap aluminium was melted for recycling, large amounts of primary aluminium had to be added to achieve the desired alloy composition for specific applications such as window frames. However, producing primary aluminium from bauxite is an energy-intensive process. Thus, finding a way to recycle aluminium efficiently without adding primary metal is a significant breakthrough. The recycling process. The recycling facility in Dagen has developed an advanced method to separate plastics, metals, and different aluminium alloys efficiently. The process involves multiple stages. Shredding and sorting. The first step is shredding old window frames and other aluminium products using powerful shears and shredders. Magnetic and eddy current separators extract metal screws, hinges, rubber, wood, and plastic, leaving behind mostly aluminium. Refining aluminium scrap. Even within aluminium scrap, there are different alloys. For instance, aluminium window handles and rivets often contain heavy metals such as copper and zinc, which are unsuitable for window frame production. To remove these impurities, a special X-ray transmission machine is used. The machine scans the shredded aluminium pieces and identifies unsuitable alloys. The identified unsuitable alloys are then removed using a system of high-speed air jets, capable of analyzing and sorting 1,000 parts per second. Final processing and melting. The sorted aluminium chips, now composed mainly of alloy 6060, commonly used in window frames, are melted down and cast into aluminium billets. The billets, measuring approximately 25 centimeters, undergo a cooling phase before being transported to pressing plants. Thanks to this innovative recycling process, up to 30,000 tons of high-quality recycled aluminium can be processed each year, significantly reducing the need for primary aluminium. This leads to substantial energy savings and a reduction in carbon dioxide emissions by over 200,000 tons annually. The German Environment Ministry has recognized this as a key technology for the metal industry, providing support through its Environmental Innovation Program. The process not only minimizes waste, but also ensures that nearly 100% of the collected aluminium is reused efficiently. The future of aluminium recycling. The engineers at the Dagen facility are continuously refining their process. Their next goal is to further improve alloy separation, ensuring that even alloys free of heavy metals can be efficiently sorted and repurposed. This would expand the perfect recycling loop beyond window frames to include beverage cans and automobiles as well. By eliminating the need for additional raw materials and improving recycling efficiency, the aluminium recycling process moves closer to achieving a fully circular economy, reducing environmental impact while maximizing resource utilization. This innovation marks a significant step forward in sustainable manufacturing and metal industry advancements. When a used oil filter is removed from a vehicle, it shouldn't simply be discarded in a landfill. Oil filters contain valuable byproducts, scrap steel and waste oil, that, when properly recycled, can significantly benefit the environment and the economy. Over 500 million light-duty oil filters are used annually in the U.S., and if even half are discarded, the waste amounts to 75,000 tons of scrap steel and over 9 million gallons of waste oil, enough energy to generate over 1.5 trillion BTUs. These numbers don't even account for heavy truck and industrial oil filters, which further amplify the issue. Generators of all sizes, from small auto shops to large industrial facilities, collect used oil filters in 55-gallon barrels. Each barrel holds between 250 and 300 filters. Once full, these barrels are transported to Lucas Lane's facility, where they are stored in a stockpile capable of holding 400 to 500 barrels. Any residual oil in the barrels or filters is drained and collected in a holding tank. Despite being drained, Approximately 40% of a filter's weight is still trapped waste oil. The filters are crushed into compact 8-inch cubes, each weighing about 40 pounds. Even after crushing, about 10% of the weight remains as trapped oil. To fully reclaim this oil, the cubes must undergo further processing. The crushed filters are loaded onto steel pallets and placed in a thermal processor, a large oven that heats them up to 1,300 degrees Fahrenheit over 20 hours. This heat extracts the remaining oil, which is reclaimed well into the 9th hour of processing. Any remaining paper and rubber components are carbonized, and the secondary chamber, operating at 1,700 degrees Fahrenheit, ensures that all smoke and vapors are completely burned off, leaving only heat vapor emitted from the stack. Through this process, approximately 700 gallons of waste oil are recovered from the filters. Around 200 gallons fuel the next thermal processing cycle, while the excess oil is sent to recyclers, often for asphalt production. The final product is clean, oil-free No. 1 scrap steel, ready to be melted down and reused in manufacturing. This 100% environmentally friendly process prevents waste oil contamination, reduces landfill waste, and provides manufacturers with recycled materials.